Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the last video, I covered the basics of what makes up a schematic and a schematic capture package, as well as the principles that define how to create a meaningful and useful schematic. If you missed that video, I strongly encourage you to take a few minutes to watch it. I've put a link up in the corner for your convenience. Now, as I said in the last video, this is a huge topic, and there's no hope of covering it in a single video or even two videos. But in this video, I hope to give you enough information to get you going. Today, I'm going to talk through the process of creating the schematic using our Mixer project in this design end-to-end video series. Now, I'm not going to expect you to sit and watch me draw every line and move every component and beautify the schematic. But I will, however, walk through the process describing the decisions along the way so that you can create your own useful schematics. I will show you how to create a hierarchical block in a multi-page schematic. We will place components, connect everything together, and in the midst of this, we have to create a new custom component. Now, if you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, one of the things that you should expect as you create your schematic is design changes. Well, stuff that you didn't quite anticipate in the initial design phase, and sometimes this is going to be subtle design changes, sometimes it'll be wholesale design changes, and sometimes, well, just adding some things that you forgot in the initial design phase. So we begin this process with a bit of planning ahead. We start by opening DIPTRACE Schematic Capture Program. The first thing we want to do is make sure that our schematic sheet size is what we're going to use. Now, I don't have the capability to print on anything but letter size paper. Here in the US, this is 8.5 inches by 11 inches, and I want 1/2 inch margins. So my drawing space will be 7.5 by 10 inches, landscape orientation. I'm going to set this up now. So we click on the File menu item, then the Titles and Sheet Setup in the drop-down menu. Select the Border and Size tab. I'm going to set my border margins all to 0.5 inches. Under Sheet Size, I'm going to set this to a width of 11 inches and a height of 8.5 inches. Lastly, I'm going to make sure the Display Titles and Display Sheet checkboxes are checked. Finally, we go down to the Apply Settings To field and select All Sheets, then click on the OK button. Well, the next question that we have to ask is, do we put the entire schematic on a single sheet, or do we use multiple pages? Well, on one hand, it would be great to have it on a single page because, well, everything is right there. On the other hand, if we are to be confined to letter-size paper, then everything gets really, really small to fit on a single sheet, and you almost need a magnifying glass to read things. For the sake of this demonstration, I'm going to create a multi-page schematic with each page confined to letter-size paper. So, what's going to go on these pages? We have our design broken up into 4 distinct function blocks. We have the input amplifiers, we have the output amplifiers, we have the indicators, and we have the power supply. Now, because the input and output amplifiers share devices and they represent the analog signal flow for the whole project, I'm going to put both of them on one sheet. The indicators and the power supply will live on their own sheets. We prepare ourselves for this by creating the sheets ahead of time. We right-click on the existing sheet tab, which is named Sheet 1, and select Rename from the pop-up menu. I will rename this sheet Input and Output Amplifiers. Now I create a new sheet by right-clicking on this tab and selecting Add from the pop-up menu. I will rename this new sheet Indicators. I do the same for the power supply function block. With our pages in place, we can start populating the schematic. Well, I always begin this process by placing the active parts in the schematic first. When I place my active parts, I often start with the integrated circuits. And in every one of these cases, I have to pay attention to two things. The first thing that I want to pay attention to is the part itself. Now, consider the base part number such as a 74 LVC2G04, which is a part number for a chip which has two inverters in it. And I ask these questions. Who makes the thing? How many are available and where are they available at? And of the parts that are available, which one has the physical footprint that I want? Now this all leads us to a very specific part that we place in our schematic, including the manufacturer and the manufacturer's part number. The second thing to keep in mind is how will this particular chip fit into the overall design from a physical standpoint. Now, we talk about our design here, which has 2 op-amps for each of the channel input amplifiers. We chose to use a chip that has 4 op-amps in the package. So, which 2 of these 4 are we going to use for each channel input amplifier, and in what order? Think physical layout. If you don't, you will get into PCB layout and have to double back and think about it anyway, moving things around to make PCB layout sane or even possible. Now, chances are you'll still have to do some of this, but here in this process, as we make the schematic, we can try to minimize some of that. Now that we have determined exactly which active parts we're going to be using in our design, we search the existing database to see if it already exists. So we can just drop it into the schematic. Now, on to the initial placement of parts in the schematic. Before I get into anything, I want you to remember that in DIPTRACE, the escape key is your friend. Every so often you may get into some mode that you don't want to be in. Maybe you don't even know what mode you're in. Hitting the escape key several times will get you back to a known state where you can resume what you're doing. When in doubt, you can always look down here to discover the mode that you're in. Now, on to our project. Our project in this series uses some quad op amps for the input and output amplifiers. I will begin with these, selecting the input and output amplifier schematic page. I'm going to search for the quad op amps using the actual manufacturer's part number NCV20074DR2G. This part number not only specifies the device, but also the physical PCB pattern associated with the device. So to do this, I click on the arrow on the right of the filter box. A pop-up window appears to enter the search criterion. In the search area field, I select all libraries. In the name field, I enter the manufacturer's part number. In this case, it is NCV20074DR2G. Finally, I click on the Apply Filter button and then wait for the search results to appear. Well, how nice! It exists in the DIPTRACE database already. We need to be sure it has the PCB footprint we want, so let's look just a little bit closer. Look at the box in the lower left-hand corner of the DIPTRACE window. This is the PCB pattern or footprint. I see SOIC14P127_865X, a lot more scribbly stuff. The part of the whole thing that I'm interested in at the moment is the SOIC14 portion. So yep, we need two of them, so we place them by first clicking on the search results, then moving over to the schematic and clicking in two places. Now, in many cases, there are no part numbers or anything placed on this schematic with the part. It's just a symbol and a reference designator. This is because not all library parts come into the schematic with a value specified. You will notice that this is the case with our quad op-amps. So we have to open the properties and assign it a value. To do this, we first select all of the parts we want to assign a value to. Then we right-click on the selected group. Then we click on the Properties option in the pop-up menu. Locate the value field in the Properties dialog box and enter the value. Now, I don't need the entire manufacturer's part number to be displayed on the schematic. I will use the base part number for the part, which is NCV20074. With that entered, I click on the OK button and it's all done. Now, this value may not be displayed in a very nice place. To move any of the text associated with a part of any kind, press the F10 key. When you hover over the text, a box will appear around the text. Click and hold on the text and drag it to where you want it to appear. When you let go of the mouse button, the text drops into place in the new location. Now, be aware that other text associated with the part may automatically choose to relocate. If you don't like where it goes, well, then just repeat the whole process on that text too. Now we jump over to the indicator schematic sheet to place the single op-amp which is used for the averaging detector. And so I will repeat this process for the NCS20071 SN2T1G, which is the single op-amp, as well as the quad comparators, the LM2901DR. And I'm loving this. Both of these exist in the database, and I've placed them in my indicator schematic page. Next, we go to the power supply schematic page to place the P-channel MOSFET, which we use for the reverse polarity protection. It turns out that DIPTRACE has the NTR0202PLT1G in its database too. Ha! This is wonderful. Well, the last active device is the DC to DC power supply module. Well, I'm not holding out any hope at all that it will be in the database, but I have to check. As expected, it doesn't exist. We will have to create this component for our schematic. Well, we begin the process by opening the component editor. In the schematic tool, I click on the Tools menu item and then the component editor in the pop-up menu. The component editor application now opens. Now, DIPTRACE organizes libraries of components in groups. The default group is the components group, which is the set of libraries that come with DIPTRACE. Now, while you can copy from these libraries, you cannot change these libraries. The group of interest to us is the user components group. This is where we add our libraries of parts. Under Select Components on the left, we select the User Components group, Now you can see what libraries you have created in the past. Now, by default, with a new installation of DIPTRACE, well, this is empty. If you do not have a library that is an appropriate repository for your new part, then right-click on the Libraries portion and select New Library from the pop-up menu. Give the library a name. Here I'm creating a library called Power Modules to hold my new part. The new library is automatically selected and an untitled component exists in it. And this is the one that we're going to be building. Now let's walk down through the Components Properties dialog box. Template allows you to choose ready-made symbols like resistors, capacitors, diodes, and the like. Now we are creating a custom part with a custom symbol, so we'll leave this at none. Name is the name of the part as it will appear in the database. This is the searchable name. I will put in the complete manufacturer's part number here for this part. RefDes is the reference designator prefix to be used for this part. This is like R for a resistor or U for an integrated circuit. This module is, well, kind of like an integrated circuit, so I will use U. Value is what will appear on the schematic next to the part automatically. Now in most cases, this is the base part number for the part, such as 74LVC2G04 for the very much longer manufacturer's part number. Because of the nature of this part, I'm going to put in the entire manufacturer's part number. Manufacturer, well, that's just exactly what the name implies. Who makes the part? With this part, it is CUI Incorporated. So that's what I'll put in here. Datasheet is a link to the location for the datasheet for the device. Now this can be an internet link or a path to a datasheet repository stored locally. Now we come to the buttons. Pattern is where we marry the schematic part to a PCB pattern or footprint. Now I will double back to this when I get to the PCB software in a later video. Additional fields is where we can add all sorts of custom fields. We can give them custom names and formats and all kinds of fun things. Now that we have all of the components' basic information entered into the properties box, we have to go to the components datasheet. We need to see what pin numbers and names that they have assigned. On page 4 of the datasheet for our DC to DC converter module, we find this lovely table. Notice that they skip pin numbers. We go from pin 1 to pin 4. We will assign pin numbers per the datasheet because this keeps the schematic in sync with the information from the manufacturer. We begin by placing 5 pins and assigning them the appropriate pin numbers and names. We do this by first dropping the 5 pins into the component and then opening the pin manager. We open the Pin Manager by clicking on the Pin Manager button in the Component Properties dialog box. Now we can reassign pin numbers and names at will. Now it feels like we can type them into the table in the dialog box, but this is not the case. We have to make these edits in the fields found at the bottom of the dialog box. We select the pin in the table and then edit the information about the pins in these fields. I enter the name and number for each pin. I will also select power in the electric field because, well, that's what they are. They're power pins. I'm going to turn on display names for all of the pins. You can do this by selecting all of the pins in the table, click on the first, and then shift-click on the last. Put the check in the box. While I have all these selected, I'm also going to change the pin length to 0.1 inches. Now we just click on OK because we've entered all the information about the pins, and we can turn our attention to arranging them for our part. Because it will live on a schematic which has a 0.05 inch grid, I'm going to make sure that my component editor is set up to have the same grid. I click on the View menu, then the Grid Size in the drop-down menu, and finally 0.05 inches in the final drop-down menu. I'm going to put the output pins on the right and the input pins on the left. This means that the output pins need to be flipped horizontally so they're facing the right way. We select the pins to be flipped, right-click on one of them, and then select Flip Group from the pop-up menu. Finally, click on the horizontal, and bang, they're all facing the right way. Now, remembering that both the input and the outputs are going to have capacitors across them, and knowing that capacitors require a total of 10 grid dots, I'm going to position these pins so the capacitors nicely fit with the part. For the output pins, I will position the 0V pin at Y equals 0, and then I will position the V plus VO and the minus VO pins at 10 grid dots up and 10 grid dots down respectively. On the input side, my pins will be 5 grid dots up for V in and 5 grid dots down for ground. Now horizontally, we need the pins to be an equal number of grid dots to the left and to the right of the central meridian. Otherwise, the component won't sit right on the schematic and you'll end up with weirdnesses going on. And after all of the pins have been positioned, then we can draw the rectangle around them. We have to be careful to maintain symmetry, again, so the part sits properly on the schematic. Click on the rectangle shape, click and drag from the upper left corner for the rectangle down to the lower right corner, and then release the mouse button. If you mess up, well, you can reshape the rectangle by clicking on and dragging the handles on the shape. Exit the Place Rectangle mode by hitting Escape a couple times, or you can right-click anywhere in the page. Select the rectangle and then click and drag one of the handles to change the shape. Now we save the library by clicking on the Library menu option and then Save from the pop-up menu. We will revisit this once we get to the PCB side of things to add a PCB pattern or footprint. With that said, the only reason that I am postponing this step is to keep all of the PCB related stuff together in one series of videos. Now, normally I complete the entire task of defining a component, including its PCB pattern or footprint. Now, once everything is saved, we're done here. We can close the component editor and return to our schematic. Well, now we go back to the power supply schematic page to place our new custom component into it. We go to the upper left-hand corner and find the Place Component section. Right now, the Components group is selected. I will click on the right arrow on the right of the Components group field and select User Components from the pop-up menu. Just below this field, we now see the custom libraries that we have created. I click on the library that contains the component that I've just created. All of the components in that library will appear in the section below the library selection. Among these entries will be the component we just created. I select this component by clicking on it. Now, when my cursor returns to the schematic, it will be dragging this component out and into the schematic to be dropped in place with a click. I'm done with the custom parts for now, and so I will go back to the components group for the rest of the schematic. Now let's see. What else do we need? Oh yeah, we have 3 identical peak detector circuits. And I'm going to use this as an opportunity to show you how to create a hierarchical block. Hierarchical blocks live on a separate sheet from the rest of the schematic. So we begin this process by adding a sheet to the schematic and then defining this sheet as a hierarchical block. To do this, we right-click on the Schematic Sheet tab at the bottom and then click on the Add from the pop-up menu. Now, alternately, you could just press Control Insert. Now, this creates a new schematic sheet by default, but it isn't a hierarchical block. Well, not yet anyway. Right-click on the Schematic Sheet tab for the new schematic page at the bottom. Hover over the Sheet Type menu option in the pop-up menu. Navigate to the Hierarchy Block menu item and then click on it. Now, you will notice that the sheet name now has angle brackets around it, indicating that it is a hierarchical block. The name that appears on this tab is what will appear on our schematics when we place this block into it. We want to change its name to something indicative of its function. Right-click on the tab and then click on the Rename option in the pop-up menu. Enter the new name in the dialog box. I will use Peak Detector. Now we get to build the schematic for the peak detectors. Click on the new schematic tab that we created for the hierarchical block. Now this circuit uses a 2N3906 transistor. Surprisingly, these do not exist in a surface mount package from anyone, from anywhere. So what am I going to do about this? Well, I could go out and choose a different transistor that has similar characteristics and exists in this surface mount package. Or I could use the leaded transistors that I already have in my parts drawers. And I think I'm just going to use my through-hole transistors because I already have, well, a ton of them. I'll just drop one transistor in my schematic. Hierarchical blocks need to have defined pins, so to speak. This is how the circuit is connected to whatever circuit it's placed in. These are referred to as hierarchy connectors in DIPTRACE. The physical location of these pins in the hierarchical block schematic determine their physical location in the hierarchical block when placed in the top-level schematic. We can rotate and flip their orientation as needed to make the resulting block functional. I'm going to leverage the global ground net for ground connection. I will place 3 of these connectors. We click on the Place Hierarchy Connector icon and then drop 3 connectors on the page. Right-click to exit placement mode. Now we want to rename each of these connectors to indicate their purpose in life. Right-click on the connector and then click on the text in quotes at the top of the pop-up menu. Enter the new name in the dialog box and hit Enter or click on the OK button. I'm going to rename mine as audio_in, DC_out, and VPP. I want my input on the left. I do not have to do anything with this connector for this. I want VPP at the top and rotated vertically, so I select it and hit Ctrl R to rotate it so that the connection point is at the bottom. I want DC out on the right and flipped horizontally, so I select the connector, right-click on it, and hover over the Flip Group option on the pop-up menu, and then click on Horizontal from the next pop-up menu. I will place the rest of the components into this schematic when I get to the passive components. Now let's place the hierarchical blocks in our schematic. Now that we have built our hierarchical block, we have to place it into our indicator schematic page. Click on the Schematic tab for the indicator schematic. We click on the Place Hierarchy Block icon at the top. Select the hierarchy block to place in the dialog box and click on the Place button. At this point, we are dragging the peak detector block around the schematic. Like dropping components in a schematic, we click where we want them to reside and drop 3 of them, 1 for each channel. Now, notice that there are no reference designators. That is because displaying them is turned off. We can easily change this by selecting all of the blocks, right-click on one of them and select Properties from the pop-up menu. Click on the Part Markings tab in the dialog box. Locate the Ref Des parameter and change the Show value from Hide to Show. Then click on the OK button. Well, like before, you might not like where it appears, so move it wherever you like it to be using the F10 key. If you don't like the reference designator that DIPTRACE automatically creates, well, you can always change that to whatever you like as well. Now, we have to start organizing the parts on the schematic. We remember as we place components on the schematic that we want left to right, top to bottom signal flow. So our 3 channel inputs will be at the left of the schematic. Now we have to think about connectors. Because this board is going to reside on the front panel and the input connectors are going to live on the back panel, the connectors will not be mounted on the PCB itself. My input connectors are just going to be a place to solder shielded cable to. So an appropriate 2-pin 0.1 inch or 2.54 millimeter pitch connector footprint will work just fine. Well, I rummaged around in DIPTRACE and looked at the various connectors available, and I found a 90131-0121 connector in the CON, which is short for connectors, rect, short for rectangular, headers, P 2.54 millimeter THT, which is through hole, vertical, non-shrouded library for the channel inputs, the mixer output, the plus 12 volt power in, and the plus 12 volt power outputs. I will drop these quickly into the schematic in approximate locations that I will adjust later. Now, I chose this connector because the hole size associated with the pins is 0.0449 inches or 1.14 millimeters in diameter, which is large enough to accommodate up to a 20 gauge wire. I also have to solidify my concept of signal flow on the PCB for PCB layout so I can arrange the right parts in the right place on the schematic. Now my op-amp chips have 4 op-amps arranged on 2 on each side. The op-amp outputs all face the ends of the chip with the inputs in the middle. With this in mind, channel 1 input amplifiers will live at pins 13 and 12, which is section 4 of the chip. The output of section 4 will feed the input of section 3 at pins 9 and 10. The output of section 3, which lives at pin 8, is the output of the channel 1 input amplifier. I will follow this exact scenario with channels 2 and 3 and the output amplifiers. I will do a quick arrangement of the parts just to get them in their respective places all lined up. And then we get to place passive components around the channel 1 input amplifier. placing passive components, this raises the very next question we have to ask. What size of components are we going to use? Are we going to use leaded components, or are we going to use surface mount components? So I choose surface mount components. One decision down. Now the question is, what size? Now I'm going to be populating this myself on my bench manually. So the smallest I want to use is a 0603. If I have trouble fitting everything on the PCB, then I could go to a 0402, but certainly not smaller. As a quick note for those unfamiliar with surface mount device sizes, 0603 means that the device is approximately 0.06 inches long and 0.03 inches wide. The equivalent to the 0603 in metric is the 1608, which is approximately 1.6 millimeters long by 0.8 millimeters wide. So I'm going to start with the resistors. I've selected the components library group. I navigate down to the resistors chip inch library. I now locate the RES_0603_M component and click on it. When I return to the schematic window, I'm dragging my resistor with me. The input amplifier requires 6 resistors, so I drop 6 instances in the appropriate spots around the respective op amps for channel 1. We'll do the same thing for the 3 capacitors associated with the input amplifiers. These will be found in the capacitors chip inch library. I place the CAP_0603_M part. Now you will also see that there's a CAPP_0603_M components. These are the polarized capacitors, which include polarization marks on both the schematic and the PCB. Lastly, we have the potentiometer, which is the channel 1 level control. More than likely, I will have to create a custom footprint for my potentiometer depending upon what I find on DigiKey. So I just need a symbol for my potentiometer, and I will assign it the right PCB footprint later. I search the libraries for the key term pot. I choose the pot component from the search results and drop this into the schematic. Now, don't be concerned with channels 2 and 3 yet. Let's just get channel 1 all prettified and everything in its place. Select all of the parts that have the same value and then right-click on one of them. Click on the Properties entry in the pop-up menu. Enter the resistor value in the value field in the Properties dialog box. Click on OK. Do this for all of the parts for channel 1. Once this is all done, we can arrange all of the channel 1 parts so that everything is nicely laid out and ready to connect everything up. Now, let's turn our attention to channels 2 and 3. Arrange the op amps in the same configuration and relative position as you just did with channel 1, leaving room between the channels. Go back to channel 1, select all of the components for channel 1 amplifiers except the op amps. Right-click on one of them and select Copy from the pop-up menu. Now go down to channel 2 and paste. Then on to channel 3. And paste again. Now all we have to do is move our op amps a bit, maybe, and align them with the components that we just pasted. The last couple things that we have to do is place our power and ground symbols. So let's start with the ground symbols. We go into the Net Ports library. We navigate down to the ground ports, and we see there is a lot of choices. Each represents potentially a separate ground. I will choose a simple GND symbol. Now I drop ground symbols everywhere I need a ground. I go back to the net ports library to find the plus 9 volt and minus 9 volt power port. Oops, none exists. So I get to create my own. So we go back, we select any one of the power ports. It doesn't matter which one, just select one that feels good. Place it in the schematic twice. Hit escape to exit place component mode. Hover over the power port symbol until you find the spot where it changes color. Right-click on it and either select the topmost entry or properties in the pop-up menu. Enter your new name for this power supply port. I will enter plus 9V for this first one, and then I'll repeat this process and enter minus 9V for the other one. I now have my plus 9V and minus 9V global power ports. Select the plus 9V port, do a Control-C, copy this, and then we run around and we paste the port everywhere we need plus 9 volts. And then we repeat this same exact process with the minus 9V net port. Now, don't forget the power supply sections for the various components. We continue this process for all of the remaining resistors, capacitors, diodes, grounds, and power ports in the design. But the one thing I haven't addressed yet are the LEDs. Well, when we're talking about LEDs, there are many, many choices. And now is the time that we have to settle on an implementation. The two most basic choices are between leaded and surface mount devices. And this decision starts with choosing where the PC board is going to reside. Now, we could have it live on the bottom of the enclosure and have all of the controls and indicators live on the front panel with the wiring connecting the two together. The other option, which is the option of choice for many products, is that the PCB lives on the back of the front panel with all of the controls and indicators on the PCB. The controls extend through the front panel and the indicators are visible through the front panel. And as I've said before, this is what I'm planning on doing. And this will affect my choice of potentiometers and LEDs. Now, back to my LEDs. With leaded devices, we can mount them at any height we want in order to have them extend through the holes in the front panel. Furthermore, machining the front panel isn't too critical because the leads are relatively flexible. Now, we could also use surface mount LEDs. The problem is the distance between the PCB and the front panel and having their light be seen through the front panel. Now, we deal with this with what are called light pipes. Light pipes are mounted to the front panel and extend through the front panel to a short distance away from the LED. These are like large-scale fiber optics, which transport the light of the LED to the front panel. Well, because I'm trying to keep this simple and I'm not too concerned about pretty looks, I'm going to use leaded LEDs for this project and mount them at the right height so that they extend through the front panel. Now I have 4 colors to choose. I have red, I have green, I have yellow, and then I have either white or blue. Now, LEDs vary in physical diameter, color, brightness, and forward voltage rating. We have to keep all of this in mind when choosing the exact LEDs to specify in our bill of materials and calculating their current limiting resistor. We don't want the green LEDs looking way brighter than the red ones or vice versa. We want them to be all the same size and the same shape. Now we can continue our work by connecting all of our components together. Well, connecting things together is so easy. We click on the place wire icon to put us in the right mode. Then we click on a pin of a component to begin drawing our wire to the pin on another component. If you want to pin a wire in place for placement along your way to the next pin, just click where you want to pin it and then continue. If you want to stop drawing your wire before you get to another pin, but want to keep what you've drawn so far, you can either click on the pin to end, then right-click and select Enter from the pop-up menu, or you can just simply hit the Enter key anywhere along the way and it does all of that. On the other hand, if you want to throw away what you've been drawing, then just hit the Escape key and boom, it's gone. Now here, I will connect everything up for the Channel 1 input amplifier. Here I'm going to proceed and go through the whole design and connect everything up. We want to name significant nets in our schematic so folks know what particular signals are and maybe a little of how they operate. To name a net, we have to be out of the place wire mode, so I just hit Escape a few times and then place your cursor over the wire whose net you want to name and it will change color. Double-click on it, enter the new name in the dialog box and press Enter. Now I will rename the significant nets associated with the Channel 1 input amplifier. Basically, I only have two of them. We have the input from the input connector and we have the output of the amplifier itself. The new name is still invisible. I mean, what good is a net name if no one can see it? We want to make it visible. To do this, we choose the spot along the wire where we want to have the name appear. Hover over that spot. The wire will change color. Right-click and select Display Name from the pop-up menu. Your net name will now be displayed in that location. At this point, I have a lot more of the same thing to do. I'm going to complete connecting everything together for all of my function blocks. And then I will get to connect my schematic pages together. Well, the outputs of each of the input amplifier channels and the output amplifiers need to get to the indicators page. So how do we do that? Well, let's start with the input and output amplifiers page. These constitute an output from this page to the indicators page. We make sure that we have the components group selected in the upper left corner of the DIPTRACE window. We select the net ports library from this group. We navigate down to the list of port components. Now there are a lot of choices here. Now we want an output port. I'm going to choose the port_out5 port and drop 4 of them on my schematic in the appropriate places. Now we have to rename these. Right-click on the port symbol, select the quoted text at the top of the pop-up menu, enter the new port name in the dialog box and press Enter. I will name my ports CH1, in other words, Channel 1, CH1_audio, CH2_audio, CH3_audio, and mixer_out. These then get connected to their respective signal sources. Our next step is to provide a landing place for these signals on the Indicators page. Click on the Indicators tab. We select port_in5 from the library and drop our 4 instances of it on our schematic. We have to rename these as before, making sure that we rename them with the exact same names we used on the input and output amplifiers page. Think of it like entering your password somewhere. These then get connected to the respective clients on the indicators page. Well, the final step in completing our schematic is to neatenize it. Add texts, boxes, tables, whatever it takes to create a complete schematic. This is an important part of the whole process. And maybe sometimes we realize that a particular component needs to move, maybe exchanging which op-amp is used where. Well, how do you do that? To accomplish this, you must first disconnect it from the circuit that it's connected to. So you right-click on the component and select Disconnect Wires from the pop-up menu. Now you can grab the component and you can move it without dragging its connections. You can then slide the new op-amp into its place. We connect the new component to the circuit by right-clicking on the component and selecting Connect Wires from the pop-up menu. Every wire which terminates on a component pin will now connect to their respective pins. Now, part of this is to move reference designators or maybe component values or whatever to make things fit nicely together. Well, how do we move these things? Well, as always, we hit the escape key a couple times to make sure that we are in default mode. Then press F10 to enter the Move Part Text mode. Click and hold on the reference designator or value that you want to move. Drag it to the new location. If you need to rotate it in the process as well, then you will press R while you have that on your cursor, and then you release it to drop it in place where you want it. Done and easy. Well, I got one last quick note for you. Maybe you want to create a bill of materials based on your schematic, a list of all the parts that you have in the schematic. Now, this is quick and easy. Click on the Objects menu item, then Bill of Materials. You can select whatever fields you want to appear in the dialog box. Then click on the Export to File to send it out to a comma-separated file that you can open in a spreadsheet program like Excel. Specify the file name and location. Done. So here's what my final schematic looks like. We see here the input and output amplifiers page. Here are the indicators page and the power supply page, the peak detector hierarchical block page. And so now go dive into your own awesome schematics. In the next video, I plan on introducing you to PCB design. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.